In fiction, teleportation is often used to travel from one place to another quickly. Wouldn't it be useful if something like this existed in real life? If you could just step into a teleporter and beam yourself wherever you needed to go? Well, something like this does exist, at least on the quantum scale. To understand how this works, we first need to introduce what a wave function is. You've probably heard of many different ways particles, such as the photon act, from miniature ping pong balls flying around to waves with a wide spectrum of frequencies. But really, the thing that best describes them is what's called a wave function. But what is this wave function? No one really knows. There's still a lot of debate on if it guides particles around, represents actual particles, or is even just a mathematical trick. But we do know how it can be used. Take, for instance, an electron. The wave function for certain particles is present everywhere, with varying amplitudes. The amplitude it has at any point gives a probability of finding the particle there. If the function has a larger value, say, here, there's a higher chance you'll find the particle there if measured. By squaring the absolute value of the wave function's amplitude, we get the probability of finding the particle there. This means wherever the wave function is 0, there's a 0 chance of finding the particle, whereas the points with the greatest amplitude, there's the greatest chance of finding it. For example, here is a simple wave function of just a single electron by itself. As you can see, the wave function is spread out at all points in space, and so the electron has an equal chance of being anywhere. Now, say a photon meets up with it. These two waves can interfere and change the wave function of the original electron. Now the electron has a high probability of being found at the high point, and very little anywhere else. This is called the wave function collapse. Now we're ready to figure out how quantum tunneling works. Imagine you have a particle next to some sort of barrier, which you can model using this ball. The particle's wave function, telling us the probability of finding it, can be calculated on both sides of the ball. However, it will decrease across it as you might expect. Crossing the barrier without tunneling, in other words just jumping over it, would take a certain amount of energy depending on the ball's height. The higher the wall, the larger the energy, the harder it is to jump over. In the same way, the larger the wall, the less probable the particle will be on the other side. The particle's wave function decreases exponentially depending on the amount of energy it would have taken to jump over, the height of the wall. The larger the barrier, the more rapid this decrease. But because of this, it'll never decrease to 0 chance on the other side. When the copper particle approaches the wall, it'll be on one side. However, when meeting the wall, the wave function can be calculated on both sides of the wall, so it has a chance of recollapsing or being measured on either side. Quantum tunneling happens when the particle is measured on the opposite side of the wall from the one it used to be on. So, that's quantum tunneling. If a particle reaches a barrier, the particle's wave function will be on both sides, hence has a chance of tunneling across. Thus, while teleporting from one place to another may currently be impossible for human-sized objects, if you figure out in the future, you'll know we'll have the weirdness of quantum tunneling to thank. Though I still wouldn't try running through any walls if I were you. Thank you for watching, and I hope you enjoyed.